Hi everyone, welcome back to physics. We were discussing one-dimensional kinematics, and this is part 4 of that series. So what we had done so far included distance, displacement, frames of reference, which had to do with reading position and Pythagoras theorem. So if you remember correctly, if you're trying to locate this point P here from this location, what you do is you measure your y distance and you measure your x distance, and that's where the location of point P is with respect to this point here, wherever you started from. So that is what frame of reference is. And then using your Pythagoras theorem, you can actually calculate the displacement of point P from this point right here, or where your origin for frames of reference started. Now that Pythagoras theorem was provided in the last video. Then we had discussed about speed and velocity, which is essentially the rate of change of distance over time and the rate of change of displacement over time for velocity. And the difference between these two and these two here is that distance is a scalar quantity. That means that it's got magnitude only, whereas displacement and velocity are vector quantities with both having a magnitude and a direction. So remember, when you're uh, writing down your answers, you'll need to provide me with a magnitude, the units of with whatever quantity that you're trying to measure, so meter per second or meter per second square, and a direction for the vector quantities, which include displacement, velocity, and acceleration. And then we also did a little bit of reading through plots. So you can use position time plots or distance displacement time plots based on what type of information you have to calculate what the velocity is for any given line that you observe. And similarly, using velocity time plots to calculate what the acceleration is. You can also use velocity time plots to work what distance you've traveled or displacement you've traveled. Um, Again, given if you know just the magnitude or if you know magnitude and direction, that will dictate if this is velocity or speed. But essentially, you can backtrack what the distance was and what you'd covered so far. Now, today we're going to be using the basic equations that we had developed in the past lecture, in the past video lecture, which were the distance or the displacement equation that was that your total distance traveled is basically the final uh, position minus the initial position, right? And then displacement is the same thing, but you've got direction added with each of those. Your speed is distance over time. Your velocity is again your displacement over time, and then acceleration is your velocity divided by the total change in time, right? Or sorry, the change in velocity over change in time during the period where that velocity change occurred. So that's what we had done up till now in the past three parts of the unit one. So what we've done so far is using these equations, you can come up with some more important functions that would allow you to present information more accurately on graphs, or it would also allow you to, uh, without using graphs, you can get more information out, more accurate information out. Now that includes, well, let's start with an example. So we're on a 400-meter drag strip, right? So let's say this is a 400 meters is equal to a quarter mile. Um, and the driver drives a car and is able to finish the 400 meters or the quarter mile within 5 seconds. Now, what can you get from this position? Now, if I were to just plot it and assuming that the car is undergoing constant acceleration, you will be covering 400 meters in 5 seconds, and that would look like something just starting at zero and constantly increasing to 400 meters in 5 seconds. Right, so that's what the position would look like, that equal amount of distances being covered in equal amount of time. Well, what can we do with this graph? That's the next part. Can we estimate what the velocity is? Can we estimate what the acceleration was? And then we can use that sort of information to develop some other important relationships or equations that can come in very handy. So let's start with this. What we've done is so far that this is the car. This is the car right here, and it is able to cover 400 meters. So that's the finish line, right? It's a checkered flag right there. And the car is able to finish 400 meters. So this is 400 meters uh, within 5 seconds, right? So what can I tell with this little graph that I've drawn? So this is 400 meters. This is my position in position axis in meters. And this is my x-axis, which is telling me the time, which is an independent factor here, and that's 5 seconds. So I can draw a line here wherever these 2 points intersect, and that's my journey, or that's my plot of how the distance is being covered during this 5 second time. Now, can I do, or can I get a velocity plot out of this little diagram right here, right? So let's start with this. Well, if I were to measure what my velocity was at this given time, or assuming that you're moving from left to right here, your velocity is given as, well, your final distance minus your initial distance by the final time and the initial time right here. So that is going to be 400 minus 0, and then 5 minus 0. So that's 400 over 5, which is equal to 80 meters per second. Now, this is, remember, this is your average velocity. So if I were to plot this out, what would happen is that you will get, this is your curve right here. This is, let's say this is velocity in meters per second, and this is your time in seconds. What is happening here is this is 5, and this is 80, let's say right here. So this is what your velocity plot is going to look like, because it's an average velocity. Because whatever the area under the curve is, this is going to tell you what the total distance is. So if I were to calculate the distance in this case, or displacement, because we know the direction, it's going to be your area under this line right here. So let me use a different color. So this is the line, this is the average velocity over the entire distance. So this is the displacement is going to be 80 times 5, which is going to give you 400 meters, right? So and if you were to do dimensional analysis on this little part right here, so it's 80 meters per second times 5 seconds. So second and second cancels out, and 80 times 5 is equal to 400, and meter is the only unit that carries forward. So that's your meter part. Right, so one thing that we do know is, now let's go back to our original plot, which is the position time plot, right? So there's a position, and there is the, that's the unit, right? And what we've done so far, if this is 400 right here, and this is 5, what we've done so far is that this is how our journey looks like, right? But the important part is, if I was to come up with the velocity axis here, what the velocity is trying to do is, if this is the velocity in meters per second, what is happening here is it starts again, the velocity starts here as well. The car was at a standstill, right? So the velocity at the start of the journey was 0. What we've said in our previous slide right here is that the velocity, or the average velocity, is 80 meters per second to get to this actual answer, which was 400 meters. Now, moving here, because the car was at a standstill at the very start, we know our initial velocity is going to be 0. So one thing we can do now is we can try to plot this. And the way to plot this is, we can draw our axis here. We've got x-axis and y-axis, where we label on our 0 point, and we start at 0, we finish at VF at t equals 5 seconds. So one thing we know, that our car started at 0 meters per second, right?
This is our velocity profile, or velocity axis in meters per second. And it finished with some velocity, which is VF labeled here, at 5 seconds. So what we have is that VF is unknown, our VI is 0 meters per second, and our final time is 5 seconds, whereas our initial time is 0 seconds, right? Um, and our average velocity is, we know that it's 80 meters per second based on this little plot that we did here, right? Um, so what can we do, or how can we find our final velocity? One thing that we can do now is, let's say that what we do know is that we started at this point right here and we finished at this point. To find what our final velocity is, what one thing that we can do is we can connect these 2 points with a straight line, right? So with by connecting these points together, what can we tell from this little demonstration here? Or what can we tell with this line? Can we find an equation for this line? Now, one thing that you could do is you can go into your Google Sheets or Excel, you can come up with a trend line, and that will tell you what the equation for this is. But then, in order to do so, you need to know what your VF value is, or you need to know somewhere some other data points along this axis, right? Which we don't know yet. So let's start with this axis right here. So let's start with a clean slate. We've got our time in seconds. We've got our velocity in meters per second. And we know that this is our VF. We started at VI, which is equal to 0, and our TI is equal to 0, and our TF is equal to 5 seconds, right? And what we've done so far is that we've said that it starts at this point and it finishes at this point. And what we've done is we've connected these 2 points together right here. And that's what we're saying, that this is how our velocity is changing over time, which is a perfectly normal assumption here. So what can we do in order to, and we also know that our V average, based from our couple of slides back, is 80 meters per second. So how can we find a formulation? Well, this is a linear increase, right? So what can we do is, well, I can say that my average velocity somehow is going to be some function of, well, V initial plus VF, right? And if this is a linear increase, I can say that it's going to be somewhere in the middle. Let's say I can do this. And that's what my V average is going to be, right? So if I do that, and then I rearrange this equation such that I'm trying to find for VF, this will change. So if I take 2 here, so it's going to be 2 times V average minus V I. Now Vi is equal to 0, so this cancels out, and my V average is 80 meters per second. So what I've left with is 2 times 80 is equal to 160 meters per second. So what I can then say is that my VF becomes 160 meters per second, and this is a perfectly fine example. Now, does the math add up? Can we start with our original plot, which was time versus position, right, in meters, which our final was 400 meters and our initial time was 5 seconds. We started at 0 for both cases, so this is our start and stop location. Uh, well, does the formula that we come up with right here, does this add up? So what we can do then is, if you go back to your initial original formula for V average, which is xf minus xi over ti, sorry, tf minus ti, I can then write this down or rearrange it as that delta x, which this is delta x, and this is delta t. I can rearrange this to say that delta t times V average. Now my V average here is, again, delta t times half of Vf plus vi, right? Um, Close parenthesis. If you were to substitute the values, what you would find is that half 160 plus 0, right? Um, that would provide you with, so 5 times half of 160, that would give you, or essentially 5 times 80 in this case, and you will get 400 meters. So the math does add up, so this is correct. So what else can we do? Now we know we've got our um, velocity time chart, right? So we've got velocity in meters per second, and then we've got time. We've covered 5 seconds, and we've done 160, and that means that we have 160 and 5, and this is what our pointer is going to be, and I can draw that line. Now, if you go back to your original set of equations, you can use the velocity time chart to come up with another important relationship, which was, or an important equation that you can derive from this, and that was to do with, well, acceleration. And acceleration is given as, well, your final velocity minus your initial velocity, or your final time minus your initial time, right? And one way to do it, this is one way to do it, so you can use that formula. Or the other way to do it, if I was to change the color of the pen again, I can take this point, and I can take this point, I can read what the x and y axis are for each. One thing I can write now is with these 2 points, this is, let's say, x2, and this is y2 for the coordinates, and we've got y1 and, sorry, x1 and y1 here, right? What I can do then is I can say, well, the gradient of this line right here, or the slope of this line, slope, uh, gradient, whatever you'd like to call it. Now, it's also denoted by the term m. When I was a student, I'm still a student, but you know, when I was a high school student, the slope and gradient was denoted by m, and that's simply the difference between y2 minus y1 over x2 minus x1. Right? So can you see the similarity between these two equations? Because you've got the y-axis up on top and you've got the x-axis on the bottom. Right? So I can do that, and that would give me the slope of this line right here. So one thing we learned is that you can derive an equation given if you know what it looks like on the plot using this equation. Y is equal to mx plus c, where c is your y-intercept. Well, where the y-intercept means wherever x is equal to 0, the y value where x is equal to 0. Well, what happens when, let's say, you don't know what the y-intercept is, or you're unable to find out what that is looking like? Now, the other part that you can do is you can actually start by this equation where y minus y naught is equal to m into x minus x naught, where y naught and x naught could be any point um, on this slope line right here. So it could be any of these points right here, which you can select from, and it will still give you the exact same equation as this. Now going back to our original case, we've already said that in this case, the slope is for any given equation or given line is given by the difference in the y coordinates by divided by the difference in the x coordinates, which for our case, for the velocity uh, time plot, is equal to, well, acceleration, right? Because acceleration formulation, as I said before, is equal to, or A is equal to difference in the velocity over the difference in the time, which is exactly the same as this. Now, using the tools that we've done in our last slide, so the equation finding tools, what you can do then is, let's say that we've got our final velocity minus our initial velocity is equal to A, our x-axis coordinates, so t f minus ti. And we can then rearrange this to look like this, that Vf is equal to Vi plus A delta t. Now, this is a very important relationship where essentially, if you know two out of, or we've got one, two, three, and four. So if you know three out of the four factors, you can work out what the fourth one is, right? So that's one thing. So this is our first equation of motion.
So what we've discussed so far is that we went from our position time plot to essentially our velocity time plot with the assumption that these 2 points are connected by a straight line, because we didn't know what the actual acceleration or all those terms were, but we're going to discuss those at another time, or at a later time. And then what we did was, using this information, we did using the relationships that we had learned from the definitions of velocity and displacement and whatnot, we were able to come up with, well, what the average velocity is going to be, which is, for a straight line, it's going to be the sum divided by the number of points, right? Um, sum of the total points divided by the number of the total points right here. So if we had another point here, you can add that into it, and that would be your average velocity and that sort of thing. And we can work on that example later on as well. That gave you this little relationship that delta x is equal to half times delta t times the sum of the different velocities, where we saw that the math added up. Now, the other part was that we went through our slope gradient part, where you extract any 2 points on a given line, and given the two ways or two methods to find the equation for an equation using that slope gradient method. You've got one part which is y is equal to mx plus c, where m is the slope or the gradient of the line, and c is the y-intercept to the point where or value of y when x is equal to 0, and the other was that y2 minus y1 is equal to m into x2 minus x1, where x1 and y1 could be any of these points, and y2 and x2 could be the unknowns that you're trying to look for. Now, using this, we were able to come up with this little equation, which is the first important part, or the first important finding of today's lecture, and that is that we've got our first equation of motion, which relates the final velocity to the initial velocity, to the acceleration, and the change in time. Now, that's our very first important relation that we've developed today. Well, what are some of the other relations that you can derive using this little equation that we've found so far? Well, what we have used so far is that delta x is a function of delta t and v average, and where v average is, well, basically the sum of the velocities over the number of total velocity points. And then we had found that, well, you can come up with this relationship. Well, what happens if you don't know the final velocity? And what I mean by this part is, well, we've already found the relationship, but what if you don't know about 2 points? Well, can we do something else with this little equation and the other equations that we'd used before to come up with a newer formulation? Well, what you can do then is, well, we know that delta x is a function of time and this average velocity. And, well, we know that Vf is equal to Vi plus At, right? So you can substitute for Vf right here, and you've got this little equation. Now you can rearrange this equation, and what you come up with is that delta x is given by Vi delta t plus half a delta t squared. Now, for instance, if you didn't know what Vf was and you didn't know what Vi was, you can use this equation then to find what VI is and what VF is going to be by using this little relationship here where my laser pointer is, given that you know what the delta X or what the difference is. So this is our second equation that we've come up with, which is that our first one was the final velocity relationship based on if you know what our initial velocity is and your acceleration and time difference are. And the second one was, well, you can find delta x or vi or whatever is missing if you have access to 3 out of the 4 functions stated here. And lastly, there's one more part that you can do is that you start off with our delta x, delta t, and average velocity formulation. Um, and you can rearrange that to find what the delta t is. Now, in our original equation of motion, or the first equation of motion where we've got this, is let's say that we don't know what delta t is. Well, we can substitute for delta t, and we've got this little equation, and after doing a bit of maths, what you will find out is that you've got this little relationship which relates the final velocity, the initial velocity, the acceleration, and the difference in the displacement. So you've got another equation. So for any given scenario, you've got 3 equations now where you've got your first relation which relates the final velocity with the initial velocity, acceleration, and time. Then you've got a second relationship which relates the total displacement with the initial velocity, the difference in time, and acceleration. So if you don't know final velocity at another one of these factors, you can use this equation. And then finally, if you don't know what the total travel time is, you can use this third relationship, which relates the final velocity, the initial velocity with the total displacement and acceleration. So if you don't know what the total time is in one of these factors, you can well use this equation to find that factor. So these are 3 important equations that you can use to basically go without plotting anything, use these equations to find what the answers are. So now I've got an in-class activity for you, and that is that I want you to derive all these equations and show each step during your derivation process. You may watch this video again over and over again to do the process. The last one I intently left out because I wanted to see if you were able to do it or not, because I've gone through 2 of those. But again, if you've got questions, please let me know. And this will be due at 5 p.m. The next topic that we were going to talk about today is freefall. Now, freefall is something that is happening under gravity. Now, gravity is an acceleration term. It is measured, or that value is nearly 9.81 meters per second square, and it acts downwards. It's a vector quantity. It's got magnitude and a direction both. So what I want you to do is, without me trying to solve it, I've given you the equations that you can use, but essentially what you can do is that you're standing on top of a 10-meter building. I want you to find out what the velocity of the ball is if you were to drop it from that 10-meter height just before it impacts the ground. Now, the next part is going to be that if you throw the ball upwards with a 15 meter per second velocity, the acceleration which is acting downwards, right? And then it will go up and then it will eventually fall down to the ground. What are the velocities when the ball reaches the top and when the ball reaches, sorry, what is the velocity going to be when it reaches the top, changes direction? What is the velocity when it reaches back at the rooftop? And what is the velocity going to be for part 2 when it reaches or just before impact at 0 meters? And then the last part was what would be the answer to number 1 would be if you were on the moon where the gravity is about 5 times less than what it is on Earth, so around 1.6 meters per second square. And that's the end of the lecture. I will be going over the last couple of examples and we will be discussing freefall a bit more tomorrow just before ending this unit, and you'll have a homework assignment that will be due in a week's time. And then that's it for today. I hope you enjoyed the lecture. You understood what was going on. If you've got any questions, please let me know. Send me an email and I'll try to answer that as soon as possible. And thank you very much. Have a good day and bye bye.